Imagine entering a realm where fluid dynamics transcends simple behavior and complex interactions dictate the fate of each droplet in a microfluidic device. In this expanded exploration of non-Newtonian fluid behavior and droplet-based microfluidic systems, we dive deep into how polymer solutions, biological fluids, and other complex mixtures influence droplet formation, stability, and encapsulation efficiency. These fluids, unlike their Newtonian counterparts with constant viscosity, changed their flow characteristics under stress, exhibiting shear-thinning, shear-thickening, or viscoelastic behaviors that challenge traditional models and demand innovative design strategies. What does this mean for droplet microfluidics? It means that engineers and scientists must navigate an intricate interplay of fluid properties and channel geometries to achieve precise control over droplet size, frequency, and content retention. At the heart of these systems is the dynamic nature of non-Newtonian fluids. In many cases, such fluids display shear-thinning behavior, where their viscosity decreases as the shear rate increases. Consider a polymer solution used in drug delivery. As it flows through a narrow microchannel, the high shear forces at the constriction cause its viscosity to drop, facilitating easier breakup of the fluid into droplets. Once the droplets are formed and enter regions of lower shear, the viscosity increases, helping to stabilize the droplet and maintain its integrity. One might ask, how does shear thinning benefit encapsulation efficiency? The answer is that it allows for a rapid formation of droplets under high shear, followed by enhanced stability when the fluid relaxes, thus ensuring that encapsulated agents, such as therapeutic compounds, remain securely inside until they reach their target. In contrast, some non-Newtonian fluids exhibit shear-thickening behavior, where viscosity increases with the rate of shear. This phenomenon can be both a boon and a challenge. For instance, a fluid that shear thickens might resist droplet breakup under high flow conditions, leading to larger or irregular droplets. However, under carefully controlled circumstances, this property can be exploited to create droplets that are more robust and resistant to coalescence. Imagine a system designed to encapsulate sensitive biological samples. A slight increase in viscosity under stress could provide an extra barrier against unwanted mixing, thus preserving sample integrity. When asked if shear thickening always hinders droplet formation, the answer is nuanced. While it may delay droplet pinch-off in some scenarios, strategic design, such as using preconditioning channels or tailored channel geometries, can mitigate these effects and even harness them for improved encapsulation. Viscoelasticity adds another layer of complexity to non-Newtonian behavior. Viscoelastic fluids possess both viscous and elastic characteristics, meaning they can store and release energy much like a spring. In droplet-based microfluidic systems, this dual behavior influences both the deformation and relaxation of droplets during formation. For example, during the droplet pinch-off process, the elastic forces may delay breakup, resulting in elongated droplets, or the formation of satellite droplets, small droplets that break off from the main body. These satellites can be problematic if they cause variability in droplet size, yet in some cases they might be collected and used if their formation is well controlled. One might wonder, why is viscoelasticity critical for encapsulation efficiency? The answer lies in the fact that the elastic component can help form a stronger, more resilient capsule wall when using polymer solutions for microcapsule formation. This property is especially beneficial in applications like controlled drug release, where a robust shell ensures that the encapsulated drug is released at the desired rate and location. Let's consider biological fluids such as blood, mucus, or cytoplasmic extracts, which often display complex non-Newtonian behaviors due to their heterogeneous compositions. In droplet microfluidic systems designed for medical diagnostics or cell encapsulation, the variable viscosity of these fluids poses a significant challenge. For instance, blood is a shear-thinning fluid. Its viscosity decreases under high shear rates encountered in microchannels, which can facilitate droplet formation. However, once the droplets are formed, the viscosity increases, aiding in the retention of cells and preventing premature mixing of droplet contents. A practical example is the encapsulation of circulating tumor cells for downstream genetic analysis. In this scenario, the shear-thinning behavior of blood ensures that the cells are gently processed without excessive mechanical stress, preserving their viability for accurate diagnostic results. When asked, how do engineers ensure that the variability in blood viscosity does not compromise the analysis, the answer is that careful calibration of flow rates and channel dimensions combined with real-time monitoring allows for adjustments that accommodate the changing rheological properties of the fluid. Polymer solutions, commonly used in the fabrication of microcapsules or in the synthesis of functional materials, also demonstrate non-Newtonian characteristics that influence droplet dynamics. In these systems, the entanglement of polymer chains can impart a significant degree of viscoelasticity, which affects both the formation and stability of droplets. During droplet generation, the stretching of these polymer chains under shear can result in delayed breakup, leading to larger or irregularly shaped droplets. Conversely, if the viscoelastic effects are balanced properly, they can enhance the formation of a well-defined droplet interface, which solidifies into a stable capsule wall once the droplet is cured or cross-linked. For example, in the creation of hydrogel beads for cell encapsulation, the viscoelastic nature of the pregel solution can be tuned by adjusting the polymer concentration and molecular weight, thereby optimizing the droplet size and ensuring that each bead is uniform. One might ask, can these polymer-induced viscoelastic effects be controlled reliably? The answer is yes. Through systematic experimentation and the use of computational fluid dynamics, CFD simulations, researchers can predict and adjust the behavior of polymer solutions, achieving the desired balance between droplet formation, speed, and stability. The geometry of microfluidic channels plays a pivotal role in dictating how non-Newtonian fluids behave. Channel design determines local shear rates and stress distributions, which in turn affect the fluid's viscosity and elasticity during droplet generation. In a narrow constriction, a shear-thinning fluid experiences high shear forces, lowering its viscosity and promoting rapid droplet breakup. However, if the channel widens abruptly, the shear rate decreases, allowing the fluid to regain its higher viscosity and stabilizing the formed droplets. Engineers often use techniques such as high-speed imaging and microparticle image velocimetry, micro-PIV, to map these shear gradients and optimize channel layouts. For instance, a flow-focusing device designed to process a non-Newtonian polymer solution might incorporate a series of tapered channels that gradually adjust shear forces, ensuring that droplets form consistently and that encapsulation efficiency is maximized. When questioned, how does channel geometry specifically enhance droplet formation in non-Newtonian fluids? The answer is that by carefully designing the channel dimensions and curvature, engineers can create controlled environments where the fluid's rheological properties are exploited to produce droplets of uniform size and stable encapsulation. Surfactants often work in tandem with non-Newtonian fluids to further refine droplet dynamics. In many microfluidic systems, surfactants are added to lower the interfacial tension between the dispersed and continuous phases, promoting the formation of clean, uniform droplets. When dealing with non-Newtonian fluids, the selection and concentration of surfactants become even more critical. For example, a polymer solution may require a surfactant that not only reduces interfacial tension, but also interacts favorably with the polymer chains to prevent unwanted aggregation or phase separation. In a practical scenario, consider the encapsulation of a protein-based therapeutic within a droplet formed from a non-Newtonian solution. The surfactant must be biocompatible and effective at maintaining droplet integrity, even as the protein molecules interact with the polymer matrix. When asked what happens if the surfactant concentration is not optimal, the answer is that insufficient surfactant can lead to unstable droplets that coalesce, while an excess can form micelles that interfere with droplet formation, reducing overall encapsulation efficiency. Thus, achieving the correct balance is paramount. Real-world applications of non-Newtonian fluid behavior and droplet microfluidics are as varied as they are impactful. In the field of tissue engineering, hydrogels, typically non-Newtonian fluids, are used to create microenvironments that support cell growth and differentiation. These hydrogels often exhibit shear-thinning behavior, which facilitates their flow through microchannels and enables the generation of droplets that serve as miniature scaffolds for cells. Once the droplets are formed, the increased viscosity helps maintain the structural integrity of the hydrogel, providing a stable environment for cell proliferation. For instance, researchers have developed microfluidic devices that encapsulate stem cells in hydrogel beads, where the bead's uniform size ensures consistent nutrient diffusion and waste removal, ultimately leading to better tissue regeneration outcomes. A question that arises here is, how do these hydrogel properties affect long-term cell viability? The answer is that the carefully balanced viscoelasticity and shear-thinning behavior of the hydrogel enable it to support cell viability by providing both a protective, low-shear environment during encapsulation and a stable, high-viscosity environment during subsequent culture. Another application lies in diagnostic microfluidics, where non-Newtonian biological fluids such as serum or plasma are processed to isolate biomarkers or analyze disease states. In such systems, the variable viscosity of these fluids can be a double-edged sword. While the shear-thinning property aids in the formation of droplets for high-throughput screening, the complex protein content can lead to unpredictable interactions at the droplet interface. To address these challenges, engineers have developed protocols that combine precise flow control with tailored surfactant formulations, ensuring that each droplet encapsulates a representative sample without significant variation. When asked, why is monodisparity so crucial in diagnostic applications? The answer is that uniform droplet size ensures consistent reaction conditions in each microreactor, which is essential for accurate quantification of biomarkers and reliable diagnostic outcomes. Industrial applications also benefit from an understanding of non-Newtonian fluid behavior in droplet microfluidics. In the formulation of consumer products, like cosmetics, and food emulsions, the ability to control droplet size and distribution directly impacts product quality and performance. For example, in the production of a cosmetic cream, a non-Newtonian oil phase may be processed into fine droplets that, when combined with an aqueous phase, create a stable emulsion with a smooth texture and extended shelf life. Here, the careful adjustment of flow conditions and surfactant concentrations ensures that the droplets do not coalesce over time, preserving the product's consistency. The question then becomes, how can manufacturers ensure consistent droplet formation in large-scale production? The answer lies in scaling up microfluidic principles, using parallelized channels, real-time monitoring, and automated control systems to maintain the same delicate balance achieved in laboratory settings. Emerging technologies continue to push the boundaries of what is possible with non-Newtonian fluids in microfluidics. Advanced analytical tools such as high-speed cameras, micro-PV, and in-situ rheometers provide unprecedented insights into the local flow fields and stress distributions within microchannels. These tools allow researchers to correlate specific rheological properties with droplet formation dynamics, enabling the development of predictive models that can guide the design of more efficient devices. One might ask, how will these predictive models impact future microfluidic device design? The answer is that they will allow engineers to simulate and optimize device performance before physical fabrication, reducing trial and error and accelerating innovation in fields ranging from personalized medicine to advanced material synthesis. In conclusion, the behavior of non-Newtonian fluids in droplet-based microfluidic systems presents a rich tapestry of challenges and opportunities. Their unique rheological properties, whether shear-thinning, shear-thickening, or viscoelastic, profoundly influence droplet dynamics and encapsulation efficiency. By carefully tailoring flow rates, channel geometries, surfactant concentrations, and polymer compositions, engineers can optimize droplet formation to achieve uniform size, high frequency, and robust encapsulation. Whether the goal is to develop advanced diagnostic tools, create innovative drug delivery systems, engineer tissue scaffolds, or produce high-quality consumer products, mastering the complexities of non-Newtonian fluid behavior is key to unlocking the full potential of microfluidic technologies. As research and technology continue to evolve, the integration of real-time monitoring, predictive modeling, and adaptive control systems promises to further enhance our ability to manipulate these complex fluids, paving the way for breakthroughs that will redefine the future of science and industry.